The title for the talk today is an invitation to celestial amplitudes. And so for the outline for this talk, I'm going to go through a brief motivation and then focus a bit on asymptotic symmetries, kind of the motivation for actually going to this basis that we're going to call celestial amplitudes, and then talk about the dictionary and some open questions. And for the second part of the talk, you guys are fortunate enough to have my former office mate and awesome colleague, maybe not directly collaborator, Prahar, who's done a lot in that area. So great. Okay, so the moral of the story, or the thing that we're all after, is wanting to learn something about quantum gravity. And the kind of nice thing about this approach, this celestial holography, which emerged from the soft physics story with Andrew Strominger and all of his grad students, and now a lot more people are getting involved, is that there's kind of two ways that one could go about it. One could look for some alternative description instead of the quantum field theory in the UV, so like some string theory, or one could even try, in the hindsight of having successful examples like ADS-CFT and other examples of applications of the holographic principle, starting from the IR and building up from this large scale structure of your space-time. What are the asymptotic symmetries? Can I match that symmetry to the start of a holographic dictionary? And that's the approach we're going to follow. So the beautiful thing about it is we're going to see is that if we look at very large scales and very large, so large distance scales, very low energies, there's a very rich symmetry structure associated to what are called asymptotically flat space-times that are going to give rise to a way to, or at least point towards reorganizing how we look at scattering. And so that's the moral of the story here. And why the name celestial holography, as I was introduced with, or celestial amplitudes. So we're going to be guided by the holographic principle. So the starting point is going to be, we're looking at the fact that we're basically in 3+1 space-time dimensions and cosmological constant close to zero. So we're going to assume it is zero. And we're going to look at the boundary of that space-time and try to see if we can see how, like, some sort of notion of how we would apply the holographic principle to that, looking at assigning some degrees of freedom to the boundary that would encode gravitational scattering in the bulk. So the idea being some quantum theory of gravity can be described by a lower dimensional theory without gravity. And we're going to look at the kind of paradigm of the successful examples that we know from ADS-CFT and try to push that to the flat space example. So on the one hand, you have this kind of very grand example where you actually have an understanding of both sides of the duality. And so if you just took the point of view that what we're doing is just the flat space version of that, it's a little bit, could be considered a little bit lackluster because we don't know the string theory origin. That's going to be one of the open questions at the end. And we don't necessarily understand both sides of the duality intrinsically. So one motivation, and like maybe some way that it's presented, is that, okay, we want to apply ADS-CFT to some astrophysically relevant context. And so one could use actual ADS-CFT in the Kerr CFT context. One could try to generalize to a de Sitter background and look at cosmological scales. Or if we're happy with particle physics experiments or gravitational wave detections, that whole range is lambda equals zero. So that's where asymptotically flat space-times or vacuum, zero cosmological constant, but non-trivial matter stress tensors are relevant for a very large scale of physics. And so if you're an ADS-CFT fan and you want to say, like, how can I apply this machinery to that very large scale of astrophysically relevant examples, then one could say, okay, let's look for some program of flat space holography. But what I want to kind of advocate today, and why I called my talk Celestial Amplitudes, is that in some sense, the framework that we're building up is perhaps a better thought of as a new take on the S-matrix program, in the sense that, right, the data that we have is you're sending something in that's on shell, getting something out that's on shell, and you have your quantum mechanical theory, in this case, a quantum gravitational theory that's governing the scattering process that's happening. And so in some sense, at least in this understanding of a dictionary between quantum gravity and some dual theory living on this boundary, we're basically going to be re-encoding in a holography inspired or CFT inspired way the external data for this S matrix. And so I think that it's also natural, as far as like two kind of pillars of what you were thinking we're building off of, is like the S matrix is already somewhat holographic in the sense that it's a function of on-shell data, and we want to like either look for self-consistency conditions. So if we try to say, like, what's a consistent S matrix, a quantum gravity S matrix, that would basically be the analog of the dual theory. Like, what is this, like the rules for this intrinsically celestial CFT guide? Or if we want to use that to then probe about the bulk or interesting things happening in 3+1 dimensional asymptotically flat spacetimes with quantum gravity, that's the question of asking what features these interactions should have. So that's the kind of framework to have in mind for, I guess, how I would see this larger program. And then let's get to what I want to talk about. So
sorry, very quick question, just to make sure I'm on track. it's always dynamical gravity in the bulk. So it's the S matrix program, but with dynamical gravity.
Exactly, exactly. Now, I mean, the thing about it too, so the funny thing is, like, a lot of times when we're playing with these toy examples for these celestial amplitudes and things like that, we will restrict to sectors without gravity. But the all the interesting physics from the point of view of like having a stress tensor, and I think that we can have this CFT, so beyond like the global conformal symmetry transformations, are coming once we add gravity. Now, there is already like some interesting stuff with Kac-Moody symmetries that are without the gravitational sector, but I think that the whole notion of, I think a lot of the power is going to be coming from the fact that there is gravity in the bulk. So we don't expect, for instance, like even though elements of the perturbation theory, like this is mostly kinematics, but like follow over without having gravity in the bulk, the interesting self-consistency of the theory is going to come from quantum gravity being there. So it's going to be dynamical gravity. Yes, yes.
Thanks.
Great. Okay. So celestialography is this proposed duality between gravitational scattering and asymptotic spacetimes, and a CFT that's living on the celestial sphere. So the celestial is the fact that I'm looking at the night sky, I'm seeing light from stars in different directions in the night sky coming towards me, and that's going to be coming from past null infinity. Or basically, I mean, like they're not actually at null infinity, but if you trace back the freely propagating radiation by coming towards you, that would go to this boundary component, which I'm going to introduce in a couple of slides. So then celestial amplitudes are going to be scattering amplitudes or S matrix elements in that basis where they transform like conformal correlators. And just to keep in mind, so I'm taking each of my external particle states, which are normally momentum eigenstates, or would basically be to a good approximation when I'm preparing these wave packets that LHC. I need to do some sort of change of basis so that to get me to these conformal correlators. And the nice thing about that is, so basically that's just how they transform into the Lorentz group. And of course, Lorentz transformations of Minkowski space are acting as global conformal transformations of the celestial sphere. So when it comes to just mechanically taking us from a scattering basis where this will work, which is going to be, I guess, the beginning of part 3 or the end of part 2 of the talk, it can be done basically because it is a statement about just different representation of the same symmetry algebra. But the power of this framework is that it's not just the Lorentz transformations, that there's actually these infinite dimensional symmetry enhancements, both of the space-time sense and then also in gauge theories, that first of all, you want to somehow take advantage of. So that's part of the motivation we're going to see. And then the second thing is that they naturally rearrange themselves in terms of two-dimensional currents. So the theme for this part 2 of the talk, which is asymptotic symmetries, which again, pointing to my awesome colleague Bahar, has also worked a lot on this and the first papers on this stuff, is that these infinite dimensional enhancements of Poincare are going to point to a natural change of basis. So the whole program of celestial amplitudes being in this boost basis is coming because that is hinted at by some sublating soft graviton theorem, which is going to encode a word identity for an infinite dimensional symmetry enhancement. So I'm going to put that in slides. So it's not just one sentence you heard, and let's go through. So I was talking about flat space holography. So our cosmological constant is 0. Now, once we have non-trivial matter sources, of course, our metric is not going to be the flat metric anymore. So we're not just going to have this Minkowski metric. We're going to have some sources that are going to deform our metric. Now, the thing about that is, okay, so the metric itself is going to look more complicated, but if I look at the causal structure of my space-time, the boundary of that is going to stay the same for this class of space-times. So I'm drawing right now a Penrose diagram. So I guess because it's a the colloquium was specified to HEP and GR, I was like a little bit more ambitious, so I guess with like more of the equations here than the colloquium that didn't have that HEP GR like label to it. So I'll go through this a little bit slower in case depending how I interpreted that. Okay, so I have, what I'm doing right now is I'm basically I'm making a plot of the coordinates for my space-time, and I'm rescaling everything, doing a coordinate transformation so I can put it on a finite sheet of paper, and then stripping off a overall factor of the metric, because right now I just, I'm not worried about the conformal factor in this plot, but basically what I'm doing is whatever I'm doing when I'm stripping out an overall distance scale won't change the angles. So I'm doing essentially looking at a conformally equivalent class of metrics. The important thing for me is that the structure of this boundary has a null component. So I have this advanced and retarded times, which in terms of basically what would be your standard spherical coordinates with a time component, U is now this T minus R. And so it captures when radiation is hitting this null boundary. If I was a massive particle, I would go from past time like infinity up to future time like infinity eventually. So whatever trajectory I have is going to stay within a light cone. And everything that is light-like in this diagram is moving at a 45 degree even though I've suppressed basically a sphere direction, except for I've shown 2 points in the sphere, because what I want to show is that if I have a particle that's coming in from the past, it's going to go out kind of at the antipodal point in the future. And so this is my celestial sphere. So past null infinity, future null infinity, and spatial infinity, and future and past time like infinity. I'm going to look at the chat in case okay. Yes, exactly. So Aaron says half diamond, exactly. So I open up the diamond because what's going to happen in a couple slides is that there's this antipodal matching condition that basically is going to be talking about how I tie together the data from past null infinity and future null infinity. And so if I didn't show that, it might not be obvious. Like just, I mean, I guess I could draw it on an Einstein cylinder. It's a little bit even clearer way of doing it, of kind of illustrating the fact that the points that I'm matching would be where like a free wave would come through, except for it's going to be kind of a causal in the sense it's going to be near spatial infinity instead of literally like that. So that's why I've drawn it double. Good. Okay. So in particular, the point for me that I care about is that my massless data, so like my initial and final data, if I wanted to basically take a Cauchy slice and push it up to this boundary, is going to be captured by data along past or future null infinity. So whenever I look at past or future null infinity, I'm going to refer to basically that cross section, that S2, as my celestial sphere. So I'm not going to be too much of a stickler saying like the U = 0 sphere is like the celestial sphere, even though from the point of view of the fact that translations will look weird in this picture a little bit, that is also kind of a natural like attitude to have. So it's just this quotient is my celestial sphere. And I'm also going to refer to that celestial sphere, regardless of whether it's incoming or outgoing, it's the same celestial sphere, and add a discrete label, which we'll see in a couple slides, but just in case for those who are sticklers with that. Okay, so now if I want to go about and ask what are the symmetries? So the first thing I want to do with, if I was thinking I'm just going to build a holographic dictionary inspired by the successes before, so not trying to find some string theory realization and then like understand different ways of looking at that, like a compactification or whatever that leads me to the 2 + 1 dimensional flat space time. The first thing that I would want to do is if I said there's some theory on the boundary that's going to encode this physics, is match symmetries on both sides. And so amusingly enough, the question of what are the symmetries of this space time is something that's maybe more subtle than what you might appreciate from like how we normally would, I guess, start from a quantum field theory course and talk about representations of Poincare. So back in the 60s, Bondi, Vanderburg, Metzner, and Sachs were addressing the question of what are the so-called asymptotic symmetries of asymptotically flat space-time. So let's break down those two words. So basically, I am looking at the incoming or outgoing. So in this case, it's that fixed R and fixed U, like basically I'm taking R to infinity, looking at fixed U. So I'm at future null infinity. I'm looking at the outgoing radiation, so the state of my system and the out state. And what I'm doing is I'm looking at how the metric is going to behave for some class of spacetimes. So what Bondi, Vanderburg, Metzner, and Sachs did is they picked a convenient gauge that's good for looking at outgoing radiation. And then the form of the metric that I've written down right here has basically already been solved for in terms of the free data. So for now, the point I want to mention is the first line is the flat metric and these retarded spherical coordinates. And then the second line, you have mass terms, which can be angle dependent because, and also, so basically, let me just point out that this would be like the analog of the mass of the system. There's an angular momentum term that's a bit like sublating to what I've written here for the sake of space. And this CZZ, and the same thing with the bar, is is capturing the radiation. And so in a couple of slides, we're going to see that there are extra, basically like Gauss's law constraint equations on the U or time evolution of this bonding mass in terms of the radiation, and that's going to play an important role. But the thing here is that essentially for some saying that my cosmological constant is vanishing, this is the asymptotic structure of my spacetime. There's an interplay between first of all, you've made this gauge choice. You're trying to actually get rid of all of your gauge degree of freedom. You have a notion of the physical fall-offs. So if I had something that was overleading an R and dynamical, it would correspond to, for instance, like some sort of infinite energy configuration or something like that. So the kind of assumptions, so you can basically solve Einstein's equations with some stress tensor. And when you're solving Einstein's equations, you need to specify some order in R fall-offs to the stress tensor if you want to solve it order by order in R. So that's what's happening. And so basically what's happening also is that if I say that my physical fall-offs are essentially like how the stress tensor is supposed to behave, that's going to affect also the physical fall-offs of the metric when I'm trying to find a solution. And basically eventually I kind of get to the sweet spot where I have this like form of the metric solution. And then I can ask, okay, so let me do some diffeomorphisms and see what diffeomorphisms preserve these fall-offs. And so one point of view is what you might hope that, okay, well, I had a flat space-time to begin with, and then I perturbed it in some sense. You would be nice, even though I don't have the full set of isometries of Minkowski space, to see that translation invariance is somehow realized in gravitational scattering, or like same thing with Lorentz invariance. And so the problem that one has is that one already knows that one can't look at actual isometries of the metric, but one can hope that basically because I am now like looking at something that preserves a class of fall-offs, so it's a much larger, in principle, symmetry group, that I could still have Poincare in it. But amusingly enough, you actually get much more than Poincare. So the asymptotic symmetry group is going to be amongst these residual diffeomorphisms that preserve that 1/r set of fall-offs that I wrote on the previous slide, the ones that act non-trivially on the boundary data. So the asymptotic data being for me, like the fact that CZZ there is encoding the radiation. So CZZ might shift, but it's not gonna, the order in R's are preserved. So what the asymptotic symmetry group is going to be is those allowed symmetries mod ones that fall off at infinity. So they never kind of act on that data at the boundary, they're subleading in R. So what they found, so what boundary value and Sachs found in the 60s is that it's much larger than Poincare. So in the number of generators is infinite in the following sense. So what BMS considered were these super translations, which if I look at the night sky and I look at every direction on it, I'm allowed to basically independently translate those generators. Right now I've written the restriction to the large R limit just because it's simpler to write down and intuit like what it's doing on this boundary. But there's also subletting corrections here. And so the second thing, which they ignored at the time, because if you wanted to talk about something being globally defined on the celestial sphere, then what one does is one finds that basically only the Lorentz group pops out of that. So you have, instead of translations and Lorentz transformations, you have super translations in addition to the translations, and still Lorentz transformations in the BMS story. But once you're allowing yourself to have punctures on the celestial sphere, you can have any meromorphic function. And so what Barnich and Trosser, and also we were, I guess others have adopted, is to look at these meromorphic guys too. There are, like, for those who do this like a lot, there's also this question of like diff S2 versus Virasoro that one can kind of try to play with this. So what I want to point out is that from the point of view of the asymptotic symmetry story, there's this kind of delicate balance between what you're saying is physical and then what symmetries you get. So if I somehow relax some of my boundary conditions, I would find a larger class of symmetries. And so the thing is that like one could go to issues of like well-posedness or like it's like some initial value form or things like that to try to like understand what physical solutions I really want to be considering. But I guess the kind of interesting thing about it is somehow what Andy and others are basically doing is we're letting the perturbative S matrix kind of hint to us which symmetries we should be considering. And so that's a beautiful part of it. So a key observation by Strominger, and of course—
Can I ask a
yes.
trivial question before you go on?
Yeah.
What happened to Van der Berg? Why did his name get dropped from the—
I know, I think it would be BBMS. I think that's kind of cute, but like, I don't know. Do you think there's actually more, there might have been a more sociological thing, because I think sometimes people actually call it Bondi Vandenberg, they call it Bondi Metzer Sachs. I think I've said Vandenberg name so many times that I can't even say that straight, but like if you go on Wikipedia, they do drop him in a very like literal, like it's gone, not just the B's have been combined. So I don't know.
Oh, guy.
Was he a grad student? I don't know if there was some sort of sociological thing. Okay. We can make a bold B or something to indicate there's two of them. There's two there. And Sachs is kind of doing his own thing, like it's, yeah, anyway. So good. So now with that history, or not history, but speculation about this, like sociology of that in mind, let us point out that basically the interesting thing that Strominger, so this is a very old story coming in from the 60s, and then maybe with some recent-ish work, I think like there's a like part of a paper by Banks and others who were kind of on the gravitational side. So like this Brussels group looking at these asymptotic symmetries again, and the symmetry algebra, if I try to extend this Lorentz group, which is a bit more recent. But basically this, at least for the leading soft theorem, the story is quite old, that there would be a BMS symmetry group that one should consider for scattering. So what would it mean if I am just like opening up my quantum field theory book, talking about some quantum field theory where I am perturbatively adding in a graviton? Okay, so the kind of beautiful thing about what Andy and then also Prahar's on one of these like first papers, like showing this for the leading guy, which is awesome, are showing is that basically I can look to this perturbative S matrix to signal whether or not I have this asymptotic symmetry. And so the thing about that is that basically, maybe I should have written that equation down on the slide, and in hindsight, for what I'm going to say right now, is that when I look at the symmetry transformation of like pulling along this vector field flow, I am going to shift inhomogeneously my radiation part of the metric, my CZZ. And so what's happening is that basically I can see that mechanically, so what's basically what's going to happen is the following. So the fact that there's a soft theorem where I have this factorization between, okay, I've added an extra graviton to my system, and that's related to the amplitude without a graviton, is mechanically the same thing as this equation on the left, which would be a ward identity. So let's unpack in this kind of compact set of equations what I mean by that insertion. Okay, so say I just take a Cauchy slice and I'm in a gravitational theory, so it's gauge theory, so my charge is codimension 2 now. So what I've done basically is if I just had some sort of smaller volume of space-time, so I wasn't actually looking at infinity, then I can take that slice and I can push it up towards this, like say, causal diamond, the future part of that causal diamond, or I can push it down. And because the data at the boundary is the same sphere, then those should be equal. Now, the tricky thing about it, say I want to really go to null infinity. When I go to the past limit of future null infinity, so let me look this slide. When I go to the past limit of future null infinity versus going to the future limit of past null infinity, that's actually an infinite amount of time. So there's a key thing in there, which wasn't actually, to what extent Andy just intuited it versus it was like derived at the time, is that I want to be able to basically relate the value of the canonical charge, so the bonding mass and the angular momentum of the spacetime here and here. And to do that, we need to say something about how those are related. And curiously enough, they're not actually just related like when you pull down, they're related antipodally. So that's why I opened up that third. So basically, here I've only written down the plus version of it, but I have some, so I'm looking at super rotations because that's kind of my baby. The angular momentum aspect and the bonding mass aspect evaluated on future null infinity near the past of it. And so if I think of this like space, this Cauchy slice is hugging null infinity, then basically that's like the boundary of that. So this is the codimension 2 boundary of, so it's codimension 1 of the Cauchy slice, but codimension 2 and then space-time. That is where I am measuring the charge for that slice. Now, with the antipodal matching condition, then I can say the same thing about the past, which is again the subtlety about the infinite amount of time between, like at spatial infinity. But given that, then, and this would be intuitive from the point of view of this like finite causal diamond, I am basically just saying that this boundary data for like what measures essentially the total mass during the momentum, but now there's an angle dependence because I'm not looking at just one static configuration. I can like basically very far away superimpose a bunch of boosted masses, which are going to have metrics that have, so like in the E&M case, if I had a boosted charge, there's an angle dependence of the Coulomb field. And so essentially I shouldn't expect the analog of these bonding mass and angular momentum aspects to just be like zero modes on, or like very low spherical harmonics. They can have an arbitrary angle dependence. And now I am basically matching that at this boundary, like this boundary of my Cauchy slice. And given that, then I have something like Gauss's law that's going to say how the U evolution of these guys is related to the radiation going through my spacetime and any flux of stress tensor that's leaving null infinity. And so Gauss's law gives a constraint equation, which then just takes this relation between this antipodal matching to a statement about radiation and matter flowing through. If I had massive matter, there would just be basically extra terms at like the other boundary of future null infinity. So basically what I can show is that if I just plug in my constraint equations and this antipodal matching condition, given the fact that I have this canonical symmetry, then I have my charge written as a soft term plus a hard term. And I then literally just say, oh, my metric should be this mode expansion, like for like quantum field theory. And that turns into a statement about the mode operator for a single graviton insertion, say. So basically the thing from Strominger is that, so like the takeaway here is I can look at a soft limit of scattering and equate that expression, the fact that there is that expression, to a ward identity for an asymptotic symmetry. And that's quite powerful because, okay, so normally, at least when I like first learned, actually, I think we were using Prahar's notes, amusingly enough, for our quantum field theory course, even though someone else was my TA at the time. When I was learning about soft theorems, the way that they would kind of motivate it would be like, okay, look, so you have this expression for these soft theorems. If I take the polarization tensor and I push it, like change it by Q, then you see that global translation invariance is going to make this thing basically like not the invariant. So it's basically going to sum to 0 or something like that. You have like the momentum conservation comes in here, the Q, so whatever, you're going to see one factor cancels, and then you have like sum over momentum, which is conserved, so 0. So now the fact that these like asymptotic symmetries are somehow acting in a funny manner. So what the asymptotic symmetry is doing is it's not just translating each of the external states, it's also adding a soft graviton. So that's one way to think of it. And so the kind of pretty thing about it is the fact that this actual like conservation law is equivalent to this ward identity, means that if I wanted to ask this question, okay, like to what extent does my perturbative S matrix obey a larger symmetry group? So for instance, there's this debate, say on the relativity side, of do I want to include super rotations or just Lorentz transformations? Well, you can go and you can check, is there a corresponding soft theorem in the perturbative quantum field theory side of things? And the beautiful thing about it is that there is. And so this was actually, I think it's from 2014, a paper by Kachaz and Strominger, showing that there is a subleading soft theorem in gravity. And then with Kapitz and Slava, Lysov, and Andy, we showed that that corresponds to a ward identity for the super rotation, which is the one I wrote down here because I'm biased toward that. But the point that I want to emphasize here is that basically by this observation that there's this connection between soft theorems and asymptotic symmetries, one can address kind of like from the S matrix that you can compute perturbatively whether or not you should expect certain symmetries that are kind of tied into how you're assuming certain things about fall-offs. So there's a kind of way to kind of answer that question for the relativist, even if it's a bit brazen to think that you can answer a question for like these like very complicated like whatever PDE people. So that's kind of nice and rewarding. But also, just because this is a colloquium and I want to emphasize like things that have come out of this program that are useful, I want to point out that this fits into this story where there's a bunch of connections in the infrared that kind of either are a touchstone to experiment or also have this nice interplay, like I was mentioning before, between something you see in perturbative quantum field theory and something that you see as a relativist looking at asymptotic symmetries and like the class of fall-offs that you want to consider. And so this is a template. I can use it for other gauge theories, so not just gravity. And then even extend it to like whether super partners that don't seem to have a gauge symmetry. There's a lot of cool things here. But the point is the following. So I want to say that the within my soft charge and my hard charge, that soft part of it, if I looked at the classical observable that corresponds to, that's called a memory effect. Someone can go out and measure it. That manifests itself as a soft theorem because its insertion in an S matrix element has this universal form. And it's the part that generates the inhomogeneous shift of the metric. So this asymptotic symmetry story is another corner of this relation. So one thing to keep in mind, which is nice, is that I kind of gave a way for someone who studies S matrices, or sorry, the like quantum field theory and this perturbative S matrix, to say, oh, look, we should really consider the symmetry. You can actually go out and tell your experimental friends what to look for when it comes to like the kind of radiation signatures that would correspond to that symmetry being relevant, and that's a memory effect. So the kind of nice thing about it basically is if I was sitting really far away and I have a bunch of like detectors just like on geodesics, then if I have a gravitational wave pass by, there's some zero modes. And so this picture that one would normally have is that, okay, first of all, it's really hard to measure actually zero frequency. So we should be careful about that. This is difficult to measure, but people can actually are working at measuring this. There's this shift that's going to come from the fact that that wave passing through basically displaces you a bit on the sphere. And then there's other subleading memory effects that rotate you or otherwise transform those observers. And so the nice thing about it is you can see already that it's a different type of detector. It's not an energy deposition detector. It's something that's really looking for these zero modes, but that you can construct a detector that will basically look for it up to some cutoff still, but a different type of cutoff. So it's not like the fact that I'm measuring a graviton or a photon with zero frequency, it's that I'm like basically looking at a certain range of integration time. And so,
can I ask a question?
Yeah.
So the relationship between a soft theorem for gravitons and the BMS symmetry for the metric, I understand.
Yeah.
But instead, there's also soft theorems for photons.
Yes.
You can do those in a fixed Minkowski space, and you look at the fall-offs for the electromagnetic field. Is that right?
That's the easiest way. I mean, I think, there's some people who look at in particular, like electromagnetism and GR together, but like you can just ignore gravity and do the whole story and see the same structure for E and M, for instance. And there's also memory effect. There's all of it follows through. The only thing, I guess, which is when you have a supersymmetric theory, then sometimes you can also get like a spin 1/2, for instance, or a scale, some of the double copy also seems to point to like a scalar, bijoint scalar soft theorem and stuff like that. And so in those situations, like the fact that there's extra symmetries relating fields of different spin, where those spins don't necessarily look like they have gauge symmetries, I think is partially giving rise to these to the relationships you're seeing there. So yeah.
And if you take, say, just pions and you want a soft theorem for pions, is that possible in this framework, or is there not enough structure?
So there have definitely been papers on it. I think I feel like the Gauss law, like constraint version of it, is easier for me. But from the point of view, if you have a soft theorem, right? So this is the nice thing about this triangular pattern, is that for me, I know, like, when there's this gauge symmetry and I have a constraint equation, I can actually see how the soft theorem is coming out as this equation. But if I have a soft theorem, I can kind of reverse engineer, like, what is it shifting? What's its symplectic partner? And so I know people have looked at soft theorems and pias and kind of interpreted it the other way around. But I don't know if I have a good intuition for like the natural asymptotic symmetry. So one other thing to point in mind, and I think this is something that Prahar says, or was indicating he's also working on too, and something with like Laura and Andrea that we've been interested in, is when, and we'll see this in a couple later slides, there are certain soft theorems that don't have obvious asymptotic symmetry interpretations. And one can kind of try to look for what they would be by this type of setup, where you know basically what these operators are, and then you want to see what they shift. And maybe there's a sense in which you can sometimes enhance your phase space by pure gauge degree of freedom to make that true. So yeah. But either way, that it helps. Like, there's basically patterns where you can point to missing things, and then you have interesting questions to ask to like understand how does this exactly quite fit in. It's a little different. Okay, good. Prahar, want to say something? Oh,
Sorry, I just wanted to add a comment that this algorithm is that Sabrina was mentioning. As far as I know, we can only do it for single soft theorems. If you give me a single soft theorem, then I can reconstruct the symmetry. Yeah. But the soft pion theorem, the interesting ones, they're double soft theorems. Those are the interesting soft pion theorems. And I don't think it's still understood how to sort of reverse engineer the asymptotic symmetries corresponding to double soft limits.
No, yeah, I think that if you'd be on top of that a little bit more than me. I know that there's there've been some double soft papers recently, but I don't think they were looking at scalars. So that's, yeah, the best thing about it is there are still open questions in these things. And it's slightly funny because you'd think, like, so one thing to appreciate is that Prahar is kind of, I feel like, focused a bit more on the asymptotic symmetry side of the story still. Well, I'll jump to something a little bit different now. And it's a really rich story. And that's what's kind of beautiful about it, is you can go into like just the soft limits and the asymptotic symmetry in a much richer way than what I'm going to peel off and just use, oh, look, the subletting stuff there. I'm going to, basically my first paper, I'm going to then jump into celestial amplitudes with it. But there's a lot there. So yeah, definitely Prahar is the guy for that. Okay, so what I want to point out then is that basically I have, okay, so the first thing I'm saying is that I have this asymptotic symmetries, with scattering amplitudes. And then also, so with this notion of these detectors that are measuring memory effects, they're basically looking at something different than an energy deposition. And so it's kind of cute that one kind of takeaway from this, so it's not just that I can go out and have some connection to experiment, I like that. But also it gives a new perspective on why you would get for soft exchanges, so in these loops exponentiating to zero, where that zero comes from. So normally also in my quantum field theory, like first course, we would talk about wanting to look at inclusive things. So we'd say, okay, our detector really only can measure above some cutoff. So I need to make sure that when I'm computing a scattering amplitude, that I am basically looking at the sum over all things I didn't measure, right? So the thing that I measured is modulo the fact that I couldn't have measured something below a certain frequency. And so that inclusive type of observable is kind of the standard prescription for how to avoid these zeros that you get from these, so virtual exchanges as opposed to like low energy real emissions. Like that's the inclusive observables are one way to avoid that problem. But the beautiful thing about it is now we can interpret this zero as the fact that if you decided to not put any external radiation, then you're violating this constraint equation. You're like violating charge conservation. And that's somewhat the intuitive way to see that is basically if I have a point charge and I accelerate it, I know that it's supposed to radiate if it's accelerating. So it would be a very strange setup to try to arrange it so that all of that radiation goes back into the acceleration of some other charge, et cetera. So basically you're always going to have to see some sort of soft radiation, but you don't necessarily have to put it on the in states and the out states. So the thing about this setup is, first of all, you see kind of a good picture of why that sum over inclusive observables is somehow including something with the right radiation to obey this charge conservation law. And the second thing that you also see is that basically you don't need to necessarily address each of the states. You can put all the radiation in the out state, for instance, and you still obey this conservation law. So you see the flexibility from the fact that the thing you want to obey is this asymptotic charge conservation. So that's a nice takeaway. And then a final takeaway, because I want to point out, like, this part of the story is a bit older, and so there's already been kind of nice like things that we've like learned from it before I go into the celestial amplitudes full, is that when you have these symmetries, so you have an infinite number of symmetries, you can either do what I'm going to do next, which is use that to try to rearrange scattering, or you can say, can I just directly use these symmetries to constrain black hole evaporation? And so Hawking, Perry, Strominger, and lots of other papers since then have kind of addressed that question of what can I do with these symmetries when I have a horizon. So there's a lot of fun stuff there. But for the rest of this talk, and what I care about most, is that not only do you have this soft theorem equals Ward identity for the symmetry in 4D, but that the symmetries in 4D are naturally arranged in terms of 2D symmetries. And so this paper here with, again, Mitra, Capitz, Reclario, and Strominger took this Ward identity with this subletting soft theorem that, like I'd worked in before, when then Cachazo and Strominger soft theorem, and showed that there's a nice smearing of that Gauss or particular value of this super rotation, where I'm complexifying things. So I set to 0 the Y bar, gives me a Ward identity for a stress tensor. So I have a candidate stress tensor coming from a soft limit of the graviton. Now, the kind of thing about this paper, though, is that there's one little thing that they're putting on the rug right now, which is how do I have an H that's a number and not an operator? So what would happen here is basically this T is inducing a boost on the external states, is adding a soft graviton to the vacuum, and it's basically boost and rotating each of the states. And I've written it in a way that this is the cleaner way. The original paper has like a spherometric Christoffel connection and things like that too. But the thing in the rest of the talk, I'll be able to kind of avoid that by doing a particular transform. So what I want here is I want to basically diagonalize the Rindler energies. And so the way to do that is to go from momentum eigenstates to boost eigenstates. And so that's what I'm going to call a celestial amplitude. So just to keep in mind, again, Lorentz invariance is these global conformal transformations. So if I want an operator that has a definite boost eigenstate, so my H is basically delta plus J over 2, then I can just prepare external wave packets that satisfy the free equations of motion for the respective spin field. So in this case, spin 2, and that transform in a certain nice covariant way to guarantee that my S matrix elements in that basis are going to transform like conformal correlators. So it's just really a problem of the representation theory here. I want a guy for my external state. So to be an external state, it has to satisfy the appropriate equation of motion. But now once I can write a solution down that has the right transformation property, I'm basically guaranteed to then have this object that transforms like a correlator. So this is the type of transformation law I want for my wave function. And one can go about actually just like plugging it into the linear solutions to see that you can write down a solution that does transform like this up to either exactly or up to a gauge transformation. And then the states I'm preparing are just basically inner products of that state with the operator that I have in the bulk. So the nice thing about this is, okay, so it's kind of like the analog of an extrapolate dictionary. I'm taking an operator in the bulk that's acting in the vacuum create a single particle state. I'm taking inner product with my particular wave function. And if I want to be more careful about the fact that I want a quantum gravity theory in the bulk, I really should be taking that Cauchy slice to the boundary, which I can do. So I can always be looking at this a bulk operator at the boundary, so I'm safer there. It's going to be along this 3-dimensional null infinity, not an S2. But because of the transformation properties of this wave function, basically when I Lorentz boost X, I'm also transforming this celestial sphere coordinate, so auxiliary coordinate here. Then I know that that object is going to transform like a 2D operator. So these are the operators that I am basically constructing by changing to a boost basis. So a lot of this talk, I'm going to be talking about massless wave functions. The nice thing about that is that I can get to a wave function that transforms that way up to gauge transformations by just doing a Mellin transform in the energies. So whatever S matrix you have, I can just do a frequency integral as follows and get myself to a boost eigenstate. So the spin is going to match helicity in that case. So the 2D spin is going to match the helicity in 4D. And the conformal dimension is what you're trading out for the energies here. So we're going to address the spectrum in a couple slides. Now, if I wasn't massless, I can still do this. And this is, again, kind of just using the kind of cute interpretation here is that I'm basically thinking of Minkowski space as the embedding space in ADS-CFT. But kinematically, I can also think of it as momentum space too. So like I can use it on momentum space on my on-shell hyperboloid, a bulk to boundary propagator, to guarantee that that convolution of the on-shell wave function, so like that space of on-shell of p squared equals negative m squared, that hyperboloid is all on-shell. I'm using this like Green's function to give me the right transformation properties. And so one can do this also not just for the scalar, which I've written here, but for higher spin too. So kind of nice. It's just a matter of kinematics and also using kinematics in a different context, but like that people have a lot of machinery for from this embedding space formalism to do what I want to do, which is to take my S matrix element and transform it so that it looks like a conformal correlator. And again, the reason why we're doing that though is because we have now like these symmetry currents is we have basically, it really looks like a 2D CFT in some sense. Like, so not just like what the global conformal invariance, but you have these, the stress tensor candidate and things like that. So there's a reason why we want to do it because of the symmetries. And so just to point out, like mechanically doing that transform is just for the massless case, doing some integrals. So that's straightforward enough to do. And I'll show in a particular example, the 2-to-2 scattering, how to do that. And the point is that this is guaranteed because of these wave functions to transform the way that I want, especially, so the wave function transforms up to a gauge transformation in this case, but because the theory is gauge invariant, this amplitude will be the same transformation property. So this is exact. Okay, so right now I've started from a motivation in terms of holography and S matrix, and I kind of try to merge that with the story of the S matrix program. Then I went through the fact that there are these, if I wanted to create that dictionary, I would have this infinite number of symmetries. So this asymptotic symmetry story is kind of pointing me towards this new basis and giving me a reason to want to look at that basis, which is like the fact that I'm putting these symmetries front and center, and those symmetries are the symmetries that I would expect for a dual to 3+1 dimensional asymptotically flat spacetimes. So what one can do is one can either try to act like to generic questions like what are the properties of the CFT? I want to just know what the spectrum are, the symmetries and the OPE coefficients, or the data of the CFT. Or one can just take some S matrix element and start transforming them. And these two kind of routes play into each other, especially like we want to eventually have an intrinsic definition of the CFT. And I was pointing out before that basically having a description like a theory that is the celestial CFT would basically be, I'd say, like an answer to like a kind of S matrix problem, like what is this like theory on momentum space? Because now basically I just transformed momentum space to something with a little bit more, maybe not more physical intuition for this delta coordinate. That's what we have to build up, but at least the celestial sphere itself kind of is like a very like physical context. So what we're going to need to understand is basically I've changed basis, so it's not quite obvious that all of my soft theorems can pull over to this basis, but they can. Can I really see the structure of a CFT, like basically like the spectrum, and that the collinear limits are, well, so collinear limits are going to tell me the OPE data. Can I really use that to kind of bootstrap, or not, maybe not bootstrap, but I determine the full amplitude? And then also, how does good UV behavior like data encoded here? And what I want to emphasize here is that that's a little bit different, David. It's a little bit different than what you would normally see in a CFT. And we'll see, first of all, that there's some abnormalities for what these correlators look like, but then we're going to see that you do get a lot of this rich structure. And if anything, maybe it's richer than the normal CFT, and is kind of a nice way of looking at the amplitudes program, I'd say. Okay, so basically let's start with route 2, where I'm going to take an amplitude and transform it. Just want to point out, we're trading our frequencies for our external particle states. I'm going to focus on massless here for delta. Because the frequency is a continuous value, we also expect this spectrum to be continuous. And what it turns out is that the data on the principal series is enough to capture all the finite energy radiation states. But we're going to see that there's a bit of a subtlety where we really want to think of the behavior of this amplitude in this complex delta plane. So one thing to point out, even before we worry about how this amplitude will behave as a function of delta, so I have some correlators that are have locations in the celestial sphere, and then also this continuous parameterization of this weight. I want to point out that I'm probing energies at all scales. So basically, from the point of view of someone doing effective field theory, this would be a problem because, okay, I have some description for how to compute my scattering amplitude, but I really only know the theory to some cutoff scale. That's not good enough to compute the full Mellon transform, at least the actual one. That means to some approximation you can. And so what we're going to see is there's two things there. It's a good thing in the sense that, like, if there is really the symmetry interpretation, we can really use the symmetries of this theory to really constrain these amplitudes, then already we're going to basically be saying something that constrains the UV in a way that at least looks different, or like naively looks different than maybe what we'd have a handle on in momentum space. And then the other thing about it too is that there's actually going to be, if you just like this beautiful paper by Nima, Andy, Anna, and Monica, where you can see that when you truncate the theory versus when you look at the full quantum gravity theory, there's going to be a different structure. So basically the fact that the amplitude is going to be analytic in delta as opposed to have some sort of distributional support is intimately tied in to how the UV what the UV looks like. And so even if it's not a direct, like maybe it's a little bit like you're kind of just probing something about the UV and we have to understand that better, it's nice that you can already kind of start to formulate like properties that you want of this amplitude. You want this amplitude to be analytic in delta. You want to say something about the poles. That's what I'm going to say next. And so we're encoding features of this amplitude in the behavior in delta. So let's just start with the kind of way that we started with this and where we got confused by it, which is to look at the low point amplitudes. And so the very first thing you're going to see is, okay, the Mellon transform is saying, I'm integrating over all frequencies. And the kind of cute thing about it is if I just take a bunch of directions, null directions, and I want to say momentum should be conserved, that means I want this null polygon to close. And so curiously enough, that actually does just basically fix the relative sizes of each of those. So the frequency becomes a function of the directions up to a certain number of points. So what we see here is that basically I want to strip out a simplex integral because the momentum conservation doesn't care about the overall energy scales. It's homogeneous in that. And so then I have for momentum conservation and I have a simplex constraint. And so that's 5 delta functions when I'm in 4D that will fix all of the energies for a generic configuration, say up to the 5 point. So if I'm lower than 5 points, so in this case, if I'm only in 1,3 signature, basically I'm at 4 point, there will be an extra constraint on that scattering amplitude. And these constraints will still persist as like some funny support on the celestial sphere of these correlators. So I'll get to at the end, I guess, like different attitudes that we have towards that. But the first thing is like, okay, this isn't quite our grandma's CFT. So let's first look at 2 to 2. So for 2 to 2, I have my invariant scattering amplitude as a function of my Mandelson invariant. So like it's sort of S and T. And then I have my momentum conservation. So we want to think about like the amplitudes people are looking at M, but we need the full thing when we're Mellon transforming. And so what will happen is, in this way I've kind of compact, like there's a spin dependent part of it too that I've kind of brushed under the rug in this quick notation here. But basically what one can find is that if you do this Mellon transform, then you have a support that I was mentioning on the previous slide. But then one also basically sees that the this amplitude here is basically probing the Mandelson amplitude. So this is a function of S and T for all values of S. And that basically you're trading out the energy scale, this S Mandelson invariant for a weight beta, which is the sum over the delta. So the kinematics of the kinematics of the conformal invariance or Lorentz invariance has been stripped off. And what one has now is one has this object that is basically half of the Mellon transform of like the Mellon amplitudes that you think of, like that's Jabayetov and others work on. So what you see already is basically if I have some sort of EFT expansion of my my amplitude, then I can kind of look at poles in this beta, which is the sum over the deltas for the external states, and see how things change if I have like a stringy behavior or like soft behavior in the UV versus my just EFT truncation. And so basically there's some pole structure in this variable beta that will encode the EFT coefficients in the theory. So that's nice. And this is a really nice paper by Arkaniemi, Pate, Rick, Leary, and Strominger. So just I want to point out, the thing that I wanted to point out here is that we see that the convergence of this integral is tied to how this amplitude behaves in the UV. And so there's already kind of this, like, we need to understand the imprint of very high energy physics on the story. And then also the fact that these, like, the thing to be studying now would be like, how does the amplitude transform in this way behave as a function of this weight parameter and cross ratios. So that's the type of question that I guess like an amplitudes person would be interested in right now, trying to build up this theory. So the exoticness of this correlator is a bit of a confusion, but the thing is, it's really because we have extra symmetries. And so that's what I want to get to next. We have translation and variance in a theory that's only guaranteed, like at least the kinematics we're focusing on is Lorentz invariance. So what we see is the following. If I want to now look at what happens when I'm not looking at like a particular low point amplitude, but just within a larger point amplitude, I tune the position of an operator, or I actually tune the spectrum because I have this freedom to tune the spectrum, what's happening. And so one thing nice is I have soft theorems that happen at particular values of delta. So what's happening is that my low energy expansion, so if I take the frequency of one of the particles soft and I look at order by order in that frequency going to zero, that Taylor series expansion or a Laurent expansion will turn into a set of poles at values of delta. And so these residues will correspond to celestial currents, and I have factorization theorems at those poles. So we're already kind of seeing that the analytic behavior in the external dimensions is telling you something about symmetries and soft theorems. So it's kind of surprising that like basically there's something that is coming from the soft limit when you're integrating over all frequencies turns into something nice in this basis. And so that's because basically that's the soft limit that omega goes to zero is giving you a pole. It's like dominating part of that frequency integral. And so the nice thing about it is in this language, we can also look back at everything that started the story, where these different soft theorems giving currents are coming from, and the fact that they are currents where they have these special conformal dimensions where you would expect, for instance, null states if you were just doing an SL2C analysis. And if you really do, so the thing about it too is that one of the questions that David was asking was, well, sometimes you have soft theorems, you might not have asymptotic symmetries that are obvious. And so in the cases where I'm looking at like subleading soft theorems, where I think that's the most pressing issue because those symmetries are important for what I'm going to talk about later, they all fit into the structure of having, okay, sorry. Yeah, this is, wrap up soon. They all fit into the structure of having primary descendants. So basically just doing a representation theory analysis of these external states that you're preparing will tell you that there's special values of the formal dimension where you should be looking for some interesting physics. And so from the point of view of the ones that I was focusing on before, where I have these memory effects and I have like my charges and basically I know the asymptotic symmetry interpretation, what one gets is you have these nice connections between more technical details that we care about. For what I want to point out here, basically when I have, when I want to look at how, like I can look at differential equations that constrain these correlators, what they're coming from basically is that I get global symmetries every time there's a kernel in this descendancy relation. So if I extend this to the case where there's not an obvious asymptotic symmetry interpretation, if I have some sort of soft theorem that tells me that I have a radiative mode that will have a descendant that should basically give contact terms in my amplitude, then I can basically smear that with some kernel and see that there should be at least a finite number of global symmetries corresponding to it. So we get from this kind of SL2C multiplet structure a bunch of symmetries. Like, so these soft theorems are turning into the fact that like basically there's a Green's function for some sourcing for them. And for each of those, I have a certain number of symmetries of this theory. And so the symmetries, when I mean like literally, it doesn't even change the vacuum. These are global symmetries that just act on each of the operators, so I can get some differential constraint on my correlation function. And the power of that symmetry is that it actually gives us something that maybe is more powerful than what you would normally think of for just a 2D CFT. So what we're going to see is that there are actually constraints on the OPE coefficients coming from these types of global symmetries. And so that's nice. So we're tying in the story from asymptotic symmetries into this basis and then showing that it gives you there's something neat about celestial CFTs where the fact that you have this continuous values of delta can give you these recursion relations, which kind of determine the OPE coefficients in a manner that you would. So basically it's saying that there's something extra on top of the SL2C that's actually important and kind of rich and beautiful about celestial CFT. So I just want to point out that I have my currents, and whenever I'm doing, talking about the symmetry algebra, I'm looking at basically like, basically conformal contour integrals of these soft operator insertions, and I reproduce the symmetry algebra. But the beautiful thing about it then is that these collinear limits I can study in two ways. I can either literally take my splitting function, my collinear limits and my amplitudes, and then ask what the OPE data would be if I try to say that two operators approaching each other should be another operator, and by which I mean I take two particles collinear, what's the amplitude that I get after that? Or I can really try to say, from the symmetry side of things, like what should be the delta dependence of those OPE coefficients. And so I just want to close off, which I think is a beautiful result from the Ray Clario, Gan, Cade, and Strominger, which is that I could either follow this first route with like Taylor and Fedopoulos and Fan, which is I just take my amplitude, I look at collinear elements, and basically do the Mellon transform on top of it. So I'm just taking the route where I know some feature of an amplitude, I'm going to transform it, see what happens. And I get some OPE coefficients for two, say, collinear gravitons in this case. If instead I try to say that I have these symmetries, these global symmetries that I know coming from this multiplet structure, then I actually get extra recursion relations on these delta dependence of these guys. And one can, in some cases, actually solve for those, solve that recursion and get the same coefficients for these OPE, sorry, the same OPE coefficients. So that's really nice. So in this case, I just wrote down the recursion relation for the spin one case because it was slightly cleaner to write down. But you have a sub-subleading soft graviton gives you a similar constraint on this graviton collinear limit. So what I wanted, so that's where I want to get to for today, was that pointing out that basically we're still in this phase where we're learning something about how to start from what we know about the celestial CFT and learn interesting, I guess, like things about this framework. So for a while, basically what we're doing is we're looking at asymptotic symmetries and everything was just tied into the IR behavior. Then we're doing these transforms and we're just transforming amplitudes and trying to see, well, I know this about amplitudes, how does it encode? But we're starting to get a better sense of the fact that we want this object to have a certain set of this spectrum, but then poles at certain places when I take my operator off of that principal series. And understanding what those residues are, and then understanding also like how I can use the behavior at those residues, and the fact that there's certain symmetries to basically give a differential constraint for my correlators, things like that. So we're starting to get a better picture of that. And what I think is really nice about that is I think we're inching closer towards maybe trying to find examples of like a consistent, like at least a toy model for maybe we're not there yet, but for this celestial CFT, we're getting a better sense of what we're expecting for it. It's not quite a normal CFT, but with that picture, that intuition is basically feeding back into like an S matrix program point of view. And it's been a fun time. So what we focus here now is on the data celestial CFT constraints that are coming from the conformally soft sector. But the real point is this framework is nice because it puts these symmetry enhancements front and center. It's reorganizing soft and collinear elements, which should be the data of the CFT. And it's sensitive to the DPV, so it could say something interesting about scattering amplitudes that aren't obvious if you aren't using these symmetries to say something about how it should behave. So steps forward, we're continuing to expand our dictionary, looking for connections to more and more subfields. We have more amplitudes people getting on board, which is really lovely. And then, of course, an intrinsic construction. So something coming from string theory would just be icing on the cake. So this is kind of the route we've followed. We started from the asymptotic symmetries and soft dams, going to celestial amplitudes. Said a little bit about connections to experiment. And really now the kind of fun thing about it is trying to get more people involved so that we can take advantage of what they are used to doing to learn more about this framework. So thank you guys, and lots of people have been a part of this story.
Thank you so much, Sabrina, for this wonderful talk.
Thank you.
Let's see, are there any questions?
So how much of what you described is special to the world we live in, namely with 3+1 dimensions?
Yeah, okay, good. So naively, the fact that I have like this holomorphic current seems relatively special to the fact that I am going to a two-dimensional theory. But the way that it generalizes is that the statement about these null state conditions, so like kind of if you just look at the global conformal multiplet structure, you look at the, I guess the Poincare extension of this, you'll see that you have, that generalizes to higher D. So what will happen is basically like these, like the leading soft theorem corresponds to the fact that I have some, like this boosting of the mass is giving some relation between the radiation that's coming out of that and the sources. And so what you'd see is that if you looked at like a null state classification in a higher dimensional CFT, the special combinations that give you those would basically feed into being relations between the radiation at certain conformal dimensions and the sources. So there's a way to generalize a lot of the structure over to that, which is nice because that's, if anything, I think the main symmetries that are coming from these OPE coefficients are coming from these kind of descendancy type relations, I think, in hindsight. And so even beyond like the leading and subleading soft theorem, which should also generalize to higher D, you would see the ones that would give you the types of constraints and OPE coefficients. Now, I think At some point though, like obviously the fact that it's not a 2D CFT is going to make it maybe less appealing from the CFT side of things perhaps, or like the what you're writing down there. But I think a lot of it does carry over, and maybe more than I would have said it like a year ago, but I don't know if I fully appreciated it still.
Thank you. Any other questions for Sabrina?
Hi, can I ask a question?
Yes.
Yes, go ahead.
So if you go back to the first slide where the S matrix computation appears.
Sorry, can you indicate a little bit more what?
Yeah, right here, yes.
Perfect, yeah.
So I just didn't understand how did the antipodal matching condition comes into the computation? Is it an
Yeah.
ingredient?
Yeah, so the issue is,
there somehow something natural about it that has to come in?
yeah, so okay, so I want to say I was a little bit glib here because basically antipodal matching comes from the fact that this cube, this first thing is 0. So sorry, maybe I should put equal 0. So the thing is that basically the thing I'm antipodally matching is this angular momentum aspect and bonding mass aspect. The fact that there would be, okay, so if I was in a finite causal diamond, I think it's relatively intuitive that there would be an in and out version of the story because I have the same boundary and I'm pushing my Cauchy slice. So this codimension 2 boundary is still the boundary of a 3-dimensional slice that is near the future of this causal diamond and near the past. I think the intuition for the antipodal matching of this data has to do, I guess, with behavior of the theory on this conformal compactification. So if you look at the Einstein cylinder, those points would be like touching each other on the other side of the Einstein cylinder. If you look at the Penrose diagram. So basically, if I had this Penrose diagram and I wrapped the Einstein cylinder, this point and this point would be touching each other, and the degenerators that would go through that point would be antipodally connected. So the way that it's normally shown.
So, I mean, that is the case on Minkowski, but apart from a neighborhood of Minkowski, I0 does not behave that well.
Yeah, exactly. So the beautiful thing, so I think this is the kind of fun thing about it is, so Ed has 2 complaints about this framework. First one is relating into out. Like this is the singularity near spatial infinity and the fact that I can't actually, like, how would I go around it? And then the second thing is how to deal with massive states. Now, I think I feel more comfortable about the massive case because I can still do this Green's function, and maybe I should be a little bit worried about how I'm smearing things over the celestial sphere, but otherwise, like kinematically, I can do that. So I completely agree with you that I think that the cases where it's been like demonstrated are still assuming something nice about the, so it's not assuming that it's not singular near spatial infinity, but we're basically resolving, not me, but the people who've looked at this have resolved spatial infinity with a hyperboloid and basically shown that the free wave equations have this antipodal matching between the data if you go to the future limit of that hyperboloid versus the past limit. Now, I would assume that the assumptions that go into that are probably probably not rigorous enough for somebody who would be worried about like the behavior of the field, like of the fields on this conformally compactified spacetime and how it's singular at spatial infinity. But it is resolving spatial infinity and looking at the angle dependence and showing that there is a antipodal matching. So at least there's some evidence for that. I would say that I think it's a good open question to understand, I guess, how one would like try to avoid or like think about continuing around that singularity, maybe within like in this larger like Einstein cylinder as opposed to just in the Poincare patch. But the way that I guess practically I've tried to like answer the question or understand it better is to not answer it, but the way that I've been trying to probe that question is also there's a curious, like I think that there's something interesting about crossing symmetry that we can talk about because basically we have a label that's for plus or minus for an in and out state. And there's been interesting papers about going to different signatures. And so that involves basically complexifying these, like the celestial sphere coordinates. And I think that eventually we want to understand not just how to antipodally match like these charges, but also understand like why, like what does crossing symmetry manifest in this setup? Basically, like I have some amplitudes with these labels, but like the strict amplitudes maybe at tree level is crossing symmetric. And I should just be able to like change out the plus or minus label for something else and still get the same thing. And so that's something I'm actively looking at, but it's an adjacent question. And I think basically what I'm trying to say is that I think that it's a very important question to understand the connection between in and out, which is like how I connect the data at future and past infinity. And I would say that there's aspects of it that are definitely very open, but the antipodal matching has been motivated to an extent that I'm happy enough with it. But I agree that it's something that's still subtle. I think that's fair.
Okay. Yeah, thank you.